Let me get some more water, 1 second.
All right. Are you good to go, Daniel?
Yeah.
All right. All right. Well, thank you everyone for coming out to today's Exoplanet seminar. I know it's been a crazy 24 hours. I hope everyone is staying safe. But I am very grateful to have Daniel here to talk about some of his work. So Daniel received his bachelor's degree in physics at UC Davis and his master's and PhD at UC Santa Cruz. And he is now a Trotter Fellow with IREX at the University of Montreal, where he studies the interior modeling of exoplanets and the related statistics. So with that, I'll just kick it over to you, Daniel. Thanks again.
Thanks. Yeah, hi everybody. Thanks for showing up. It's even crazier than it has been recently. I will try to focus and talk about work I've been doing studying the evolution of hot Jupiters over time. And so I'm really big on taking the set of observed giant planets and trying to extract physics from them. And this is the data set that we have to work with to do that. This is all of the giant planets, including the cool ones, in mass versus radius, that have reasonably well-determined masses and radii. I think the cutoff for this plot was 50%, but it might have been a little bit lower. Relative uncertainty. And so in general, these are planets that were discovered by transit and then had RV follow-up to work out the mass. And I think it's a little bit more enlightening when you're looking at this data and thinking about giant planets to transpose the color and the y-axes here. And the x-axis, excuse me. So now we're coloring by mass, but the x-axis is the amount of stellar insolation hitting the planet. And so you can see that we have, can you see my mouse? Is that a thing? Whatever. You can see at the bottom, we've got the lower mass planets. But for the higher mass planets, there's something really interesting going on with flux. If you go to the left of that dotted line, which is about 1,000 Kelvin equilibrium temperature, you have the cool giant planets. And they don't seem to, their radii don't appear to react much to changes in the incident flux. 1e6 over there is around an Earth flux. So these are, still warmer than Earth, but not as hot as the hot Jupiters to the right of the dotted line there, who are both much larger than the cool giant planets and also seem to be very strongly correlated with the incident flux. It's not as though there's a continuous line. Like there is an effect that seems to turn on somewhere in the vicinity of 1,000 Kelvin, or at least is just swamped by some other effect below 1,000 Kelvin. So a lot of people have written papers trying to understand where these excess radii, where the large radii of hot Jupiters comes from. And part of the reason that this is such an interesting problem is that you can't really get the hot Jupiter radii that we see in this plot just by changing composition. Even if you have a pure hydrogen helium planet, that I mean, just composition-wise, that's the biggest you can get. Even if you had a pure hydrogen planet, if you were somehow able to engineer that, you can't exceed more than about 1.2 Jupiter radii. And so you can see the hot Jupiters are way above that. And if you do it by heating them, you can get to that size. But you expect that they would cool off and shrink within, a few dozen mega years. And so the fact that we're still seeing all of them there says this wasn't some one-time event. Either they're constantly being heated or something is keeping the heat inside, or both. And so to try to figure out the difference between those two categories of physical explanations, Eric Lopez, who is at Goddard, I don't know if he's in the audience right now, but he proposed an idea that we look at hot Jupiters that are around red giant stars, but that they were ideally that were not hot Jupiters before the red giant, before it moved into the red giant phase. And so the idea is that it was a cool giant planet and then it became a hot Jupiter during that transition. And so you would expect, if it had always been at the level of heating that the red giant does, because of course that dramatically raises the flux on the planet, that it would be very large. But we don't know that whether it's, well, let's see. If the thing that is heating the hot Jupiters is keeping the heat in, then a hot Jupiter around a red giant will remain as small as it was before the star moved on to the red giant phase. On the other hand, if it's a constant heating effect, then the hot Jupiter will reinflate to whatever radius is appropriate for its new stellar insolation. So he teamed up with Sam Grunblatt, and they found 3 red giants with the 3 hot Jupiters around red giants that are come with the caveat that they were probably hot before the star moved off the main sequence, but only barely. So they started out a little hot and then they became very hot. And that kind of messes up the analysis a little bit. It does seem like they probably did reinflate, but it's hard to be completely sure. I think that if we can find that perfect case, we'll have it. But an alternate approach was suggested by Hartman in 2016 in a discovery paper that almost hides the really interesting theoretical stuff he did there. So over their main sequence lifetimes, stars also brighten. And actually, they brighten by quite a lot. Enough that you might expect the hot Jupiters to grow in size over time. And so what Hartman looked at was the fractional age of the parent star, which is just the age over its expected main sequence lifetime, against the radius of the planet orbiting it. And he found a positive correlation with fractional age, which suggests that these planets are indeed reinflating over time. It's difficult to see why that would come about otherwise. But there are there's a lot of variables flying around there, right? I mean, it could be that very young planets are just generally brighter. Very young stars are generally brighter, and so the planets around them are generally bigger. So you've got to kind of dig into what other variables are involved here. So to do that, we teamed up with Dan Huber and Travis Berger to work out a uniform set of stellar ages for hot Jupiter hosts. And you can check out their work for, they they've been mostly focusing on the Kepler planets, but they're moving on to some of the other sets. For the hot Jupiters, it's kind of a mishmash of, Kepler and Corot and WASP. So we got this uniform set of ages, and now we're going to try to ask what actually predicts the radii of hot Jupiter. And this is sort of a starting point for understanding the physics going on in the background. So to do this, I'm going to make a mildly excessive use of the Bayesian information criterion. So I'm going to explain that in case you don't know anything about it. So suppose you have two models that are trying to explain the variable y, and you'd like to know which one fits the data better. Well, the Bayesian information criterion is one way that you can go about that. It has two terms. You have the likelihood term, which tells you just how well it fits the data, of course. And then you have a penalty term for the number of parameters, which scales with the amount of data logarithmically for deep information theory reasons that I don't understand. But they say that this is a good scaling factor, although they also argue about it extensively in the, anyway. Not dwelling on that too much. So this is a formula. You have two models. You can just plug it in and work out what the Bayesian information criteria number is. And the one that the BIC favors is the more negative number, because for some reason they decided that they were going to subtract off the log likelihood, whatever. In this case, the model on the right is the more negative number. It has a delta BIC of minus 15.7, so it wins. And in general, there's no hard line for what is a significant winner. In my book, once you're past 5, you're in a pretty good territory. But the statisticians really do not want to give us a number anymore after what we did, the p-value of 95%, or 0.05, if you look at it the other way. So we just have to be cautious. All right, so here's how I'm going to be using this. I have, for my set of hot Jupiter data, a model on the left-hand side. In this case, it's literally, I propose that all hot Jupiters are exactly 1.26 Jupiter radii, which is a little bit of a ridiculous model. And so on the right here, I have different variables that I might add as a power law to that model. And the delta BIC associated with adding that variable. So you can see if I just add mass here, it's not favored. It's actually a little bit better to keep this current model. The penalty is larger than the benefits. On the other hand, there's a huge benefit to including the flux in a power law, and it beats out the stellar mass and radius and the semi-major axis. And so from this analysis, you say, okay, well, the best variable to add is the flux. But the important thing to remember about this approach is that I'm looking through the set of power law models. So if it's significantly deviant from a power law model, it's not going to pick up that variable is important. So if something, especially if something like is flat and then goes up, or it goes up and then it goes down, it's going to have a harder time picking that up. And that's why I've specifically, you remember the flux radius relationship is flat and then it goes up. So I've actually cut myself off to look just at the hot Jupiters there to avoid that problem. And I'm also only looking at planets that are more massive than half a Jupiter mass, just because I've noticed that there's something interesting going on below that, but I'm just not going to try and work it out in this paper. I'm just going to focus on this regime. I've dialed this up to 11 and have produced a ton of models and looked at the Bayesian information criterion for adding variables to it, with the idea that I can construct a model by just adding the most favored variable until I don't see much of a gain. So we start out here. We have a constant model. I look at, okay, what is the best variable to add to this model? Oh, it's the flux. All right, so here's my new model. What's the best variable to add to this one? Oh, hey, look, the mass suddenly is important. Once you have accounted for the flux, the mass becomes important, and that's really interesting. It does seem this analysis is really good at picking out when variables are only useful when another variable is present or is not present. So, like for example, the stellar mass was only useful as a predictor for radius if you didn't have the flux. So it turned out the stellar mass was just kind of a cheap, crappy substitute for having the flux, which is the real information that you wanted. So I go all the way through this and I build up a model. This is the model that I personally think is a good balance between adding variables and your benefit to uncertainty. You can actually tack on the stellar metallicity if you want. I'm going to discuss why I don't do that sort of towards the end, but I think it's a really interesting relationship. You can see it's only 6 here, so it's debatable, and I will discuss the debate there. But this is the model that I'm going to be going with, this mass flux radius relationship. And so the first thing I did was I isolated the cases of hot Jupiters where the flux hasn't changed very much since the planet formed, by less than 50%. And that's a little less than half of the data set. And the idea was that this would be a control group against reinflation. These guys have not brightened enough to have significant radius reinflation. And yet, when I cut off the bottom, this bottom half or so, maybe more like a third, you actually get the same relationship between mass and radius and flux. And that's interesting because if the stellar flux was increasing over time as the star evolved on the main sequence, and you did not have any reinflation effect, you would imagine that the stellar flux would start to outpace the radius. Like the radius would stay behind and the flux would go up. And so you would expect that stars that had spent a long time evolving would have a different, at least, maybe not weaker, but different relationship with flux than the ones that had not spent a lot of time evolving, that had not brightened very much. And yet we don't see that. I was kind of expecting to have this control group and use that as my baseline model, but it turns out it doesn't matter whether you use this control group or not. And so let's see, there are some other things to look at here. The fractional age effect that Hartman talked about, I see it too. It's pretty weak. It's not, a stand. If you look at the Hartman paper, they don't claim this is a wildly useful predictor for radius. They just say it's there and it's statistically significant, and I agree with that. And to remind you, that's the age divided by the main sequence lifetime of the star. I did a control group against possible delayed cooling, where the formation heat of these giant planets initially has them very large and very hot, and then they cool down over time. And I wanted to cut that out of the data, so I looked at planets that were only larger than 3 gigayears. And you can see that didn't actually make a huge difference either. But we'll come back to discussing that. Let's see. What we do have, though, is a stellar age effect, basically. There seems to be initially, sorry, a little scatterbrained about this, my apologies. It seems that stellar age is useful for predicting radius. And interestingly, this actually, if you look into what direction the correlation points, this is in the opposite direction of the fractional age. The fractional age correlates positively, and you can't see this from this plot, or from this table. The fractional age correlates positively with radius, whereas the age correlates negatively with radius. But if you cut out the first few gigayears, the planets in their first few gigayears, that disappears. And that says to me that there is a small delayed cooling effect, potentially, in the data. But I'll discuss that more. I wanted to actually get into modeling the evolution of giant planets over time. And so to do that, well, let's start out with the age data that we got from Daniel Huber and Travis Berger. So I've plotted it here in terms of the fractional age against the radius, and then also just the raw age against radius. And I've done Kendall's tau correlation tests on the relationship for each of the panels. And so on the left, you can see that very weak fractional age to radius relationship that Hartman found in 2016. And I agree with it. It's pretty significant. But as you can see, it's, you wouldn't use this as a way to predict hot Jupiter radius. But the fact that the correlation there is interesting, and it suggests that there may be reinflation going on. On the right-hand side, you can see a really significant decay over time in the radius. And it's wildly significant. But the problem we have is that we don't know whether that's, young hot Jupiters cooling down to some equilibrium, or whether that's just, but the young guys are around, the brightest stars can't be 7 gigayears old. They explode, evolve before then. And so those have the highest flux Jupiters, and those guys are bigger. So we have this issue that we need to kind of sort out. Is it just because the younger stars are brighter, or is it actually that as they're younger, they're bigger? And so what I'm going to do is create this very simple model, focusing mostly on the idea that there is an equilibrium radius that we derive from that table that I showed you earlier. And the idea is that, originally I was going to just use the control group of stars that haven't evolved very much to work out what the radius that you will go to after a long time is for a given mass and flux. And then say that, okay, well, we're going to decay towards that radius on some time scale that is, it's an exponential decay. But the time scale could be different depending upon whether you're decaying down and releasing heat, or decaying upwards and somehow gaining heat in your interior. It could be, if there is no reinflation, then the time scale of reinflation is infinite. It just goes out forever because you'll never really reinflate. And so what this model looks like when you apply it to actual luminosity curves of real stars is this. So as the star brightens, the equilibrium radius that we got from that table analysis, it increases, and then you see a big main sequence, a post-main sequence brightening there after the star exits the main sequence, and that's what this vertical dotted line is. And depending upon what the time scale of reinflation is, you get different curves for the planet radius. So if it's a very short time scale of reinflation, you can just keep up with the equilibrium radius. And notice just how much inflation we're getting here. We're getting like 0.1 or so Jupiter radii over a lifetime of the star, and that is definitely detectable by transit methods. So it is entirely plausible that a fast reinflation timescale is something you can pick up by looking at a population of hot Jupiters. So that's heartening. It's good that stars are brightening enough that this whole thing is actually viable. And importantly, the converse is also true. If there's not, if there isn't stellar brightening, then you have a very long time scale of reinflation, and you end up with a relatively flat radius-age relationship. Once the initial heat has cooled off enough that it's below the equilibrium radius, you just end up sticking at that radius more or less um, for the rest of its lifetime. So I was interested in where planets are relative to this equilibrium radius. Are they keeping up? Are they not keeping up? And so I've added that to the plot that you saw before. And all I'm doing is just dividing by the equilibrium radius. And the important thing about this is that this removes the stellar flux effect. Or let's see, how do I say this precisely? We're now correcting for how bright the parent star is at the present date. All this is now is saying, well, relative to that mass flux radius model, where are we? Are we bigger than equilibrium or are we smaller than equilibrium? And what I find is that that actually perfectly cancels out the fractional age effect, which it should if there's reinflation and my equilibrium radius model is correct. You should just completely remove any effect, because that's what the equilibrium radius thing is coming from, is that the fractional age is sort of a crappy proxy for a change in the equilibrium radius. And so the fact that having the actual equilibrium radius calculated removes the utility of the fractional age, that says that we've got the right equilibrium radius. But really interestingly, if you plot this against age, it does not cancel out all of the effective age. So you can still see in the bottom right-hand panel that there is a small decay in the first few gig years of the radius relative to equilibrium against age. And it does seem to flatten out. It's really hard to tell where it flattens out. The data is just too noisy to really be sure. But it seems to be in those, after a few giga-years, it maybe has flattened out with big plus or minuses on that. And the negative correlation is really quite significant in this. I realize that oftentimes in these plots, I have some points that have very high error bars, but that's because I'm approaching this in a sort of Bayesian. I'm including the relatively high uncertainty planets in addition to the relatively low uncertainty planets. So at any rate, so from this, I think it seems pretty likely that reinflation is occurring. We know that it is possible to get reinflation just from the amount that the stellar luminosity increases over its lifetime. We can see that the mass flux radius relationship is the same whether or not we corrected, whether or not we include just the stars that haven't brightened very much. And oftentimes that's just low mass stars that brighten very slowly over a long time. So it's not just young stars, it's also older but low mass stars. And then we are able to find the fractional age effect that Hartmann found. But not only that, by correcting for this equilibrium radius that we found, it perfectly cancels out the this fractional age effect. Interestingly, if you try using the zero age main sequence flux, which we estimate from our stellar models, that does not cancel out the fractional age effect. And that makes sense because the fractional age effect is talking, well, how much have we brightened since we entered the main sequence? And so if you're just using the flux at the main sequence, it does give you a good general idea of how bright the star is. Certainly, you know, if you're going from an F star to a K star, you're going to have a dramatic decrease in brightness and therefore lower flux and therefore smaller planet radius. So this is still useful information we're giving it, the zero age main sequence flux. But because the subsequent brightening matters, the fractional age correlation is still there after we do it. And then finally, and rather unexpectedly, I didn't think there was going to be any significant delayed cooling effect. when I started this. It actually seems like in the first couple gigayears, there is still some formation heat hanging around inside these planets. And that's surprising because if you just run the interior structure models, which I haven't done for any of this paper, but I have done for other papers, you would really expect these things to cool down in tens of millions of years. And so it's very surprising that we're seeing it in the billions of years, unless you're one of the proponents of these delayed cooling models, in which case, aha, you're vindicated. So I wanted to talk about a little bit more about some work that we're doing from the interior models perspective that Tad Kamasic did last year, which is looking at how can you reinflate these planets. And so what he's done, and I'm only going to touch on this briefly, but is we have pressure temperature curves for the interiors of hot Jupiters in particular. And he has added in a heat source. So this could be some kind of thermal tides effect. It might be potentially the ohmic heating model. And he's added it at different pressure levels. And so you can see in the solid line before, well, actually that's the solid dotted line is something else. Sorry, my apologies. That's the convective versus radiative regions. But if there's no heating, you end up with this lower temperature planet. That's where the heating is so high up that it basically has no real effect. And then I managed to confuse myself. But depending upon where you place the heating, you end up heating the area above that, right? The heat can go up because it's convecting upwards, but it really can't go down. And this has kind of been a problem in studying hot Jupiters, is that even if you can get the heat down to, say, a kilobar, you'll still end up, oh God, which one is it? This is the problem with the plasma color map. One of these two. You still end up only heating the area exterior to that. The inside, convection does not bring heat down. That's just not what it does. And conduction is very, very weak in giant planets. So what you end up with is a not inflated interior region, and then an inflated exterior region, and a big jump in the specific entropy somewhere in there, wherever the heat is being deposited. And so you need to do better if you want to do reinflation. Something like ohmic dissipation, even if you assume it's very deep, isn't enough to do reinflation, because you would only be heating the very outside portion of the planet. And that will produce some reinflation, to be sure, but not nearly as much as you would need. If you want to reinflate the whole planet, in the bulk where most of the radius is coming from, in these 10 to the 6 to 10 to the 4 bars, you need to reinflate quite deep within the planet. That's the takeaway from this plot, and that means something like maybe thermal tides, because you can spread out the heating through a wide swath of the interior of the planet. So one last argument that I'm going to put in here, that we saw, and I promised to come back to it, so here we are, is what's going on with the stellar metallicity and the radius. So we saw in the table there was a mildly significant BIC that favored including the stellar metallicity in the in our radius models. And so if you pull that up and you plot it out, radius over equilibrium against the Z star, which is sort of the applicable way to look at it, rather than FE over H. It's just the exponential of FE over H. This is the plot you get. And I have been informed that this is not the most convincing plot in the whole world. So on the top, I have all of the planets, and you can see the Kendall-Tau test there is significant. And then on the bottom, I have just the planets that had the relatively low uncertainties, because I was sort of concerned that people were just looking at, oh my God, there's so much scatter. Well, there's a lot of observational scatter in both the stellar metallicity and the planet radius, but we do have some planets that are relatively low scatter, and so that's what I've shown on the bottom. I've been informed that that is still not wildly convincing. So I've done a whole bunch of significance tests of basically every manner that I can think of. I'm a huge fan of Kendall's Tau, and I did that first. And people have told me, oh, you need to bootstrap it. It's just being, it's being driven by a few points. So I did that, and it is still significant. I also tried Spearman's Rho and Pearson's R, and I bootstrapped both of those, and they were still significant. The weakest one was Pearson's R, because Pearson's R is only good for linear relationships, and this is exactly linear. But it was still significant. So I also did a Bayesian hierarchical model to try to see if the uncertainties included no relationship between stellar metallicity and radius. But no, it was about 3 sigma significant that the power in a power law model, that the Fe over H was non-zero. So there's actually good theoretical reasons to think this kind of relationship exists, which is that, well, if the star is more metal rich, then that means that the nebula that it formed in was more metal rich. And that led to more metal rich planets. It doesn't have to be 1-to-1. And in fact, in a previous paper that we did with Johanna Teskey leading, we actually found that it was less than 1-to-1. It's not perfectly strong. You can't just double the metal in the star and then you get twice as much metal in the planet, because planet formation is more complicated than that. But if there's more metal around, you still end up getting more metal in the planet. So I don't think this is a wild claim, but you may or may not believe it, as your will. So for my conclusions, I think that hot Jupiters seem to reinflate pretty quickly when their parent stars brighten. You can only really get that if you're heating the deep interior. And so one option is thermal tides, but that's not an exclusive thing. There's an enormous set of proposed solutions, some of which involve deep heating. But on the other hand, there is also delayed cooling going on. It's not enough to actually explain the radius of hot Jupiters, even at relatively high ages when the radius-age relationship is flat. They're still much larger than you would get for a cool giant planet. So there's got to be both heating and delayed cooling going on. So what we shouldn't take away from this is that the shallow heating models are wrong in some way. It really seems like there is something keeping the heat inside. And if you have something like ohmic dissipation or the mechanical greenhouse model, that would be really good at making it hard for heat to escape the interior of the planet. And that has the added benefit of, well, you don't need to put as much heat in per time, because it's not like building a sandcastle when the tide's coming in. You've actually got something keeping that heat in, and so you don't need to inject as much. So I think that for the future, when we're trying to understand hot Jupiter radii, we should be thinking about a combination of effects, some kind of deep interior heating, and also something near the surface that's keeping the heat from getting out. And so that's my conclusion from this, and I am out of slides, so thank you for listening.
Thank you so much, Daniel. That was great. So I think there are a few questions in chat. So Preble, I see your hands up first, and then I see the question from Nicole we'll get to next.
Hey, Daniel, great talk. Second time I've been looking at the spreadsheet, super interesting. One of the questions I had is really about the stuff you're talking about at the end. Have you thought about, would it be useful to look at, for example, offsets in terms of hotspot offsets to try to extricate, how much something like ohmic dissipation or whatever else might contribute in cases where you have other kind of factors constrained on like kind of deep dives?
Yeah, I think that there's definitely work to be done there. It's hard for me to prescribe an exact thing to go for. I think that with regards to ohmic dissipation, it's still in the running, right? Because it could be that ohmic dissipation is being a significant factor in keeping heat in. Maybe not so much on the reinflation front, but it could be causing a delayed cooling effect. And it seems like you ought to be able to see some kind of sign of that in the atmosphere. I'm not enough of an atmospheric guy to be able to tell you what that is. One thing you look at is what the intrinsic temperature of the planet is. But of course, these things are so hot that it's hard to distinguish that. But the interiors are so hot that the intrinsic temperature could be as much as like 700 Kelvin. It depends on exactly what the magnitude of the delayed cooling is. But there should be signs of this in the atmosphere. I think we've really got to still think about it exactly how we use things like hotspot moving. I think that with regards to that, because the ohmic dissipation effect is so much about what's going on in the atmosphere, there should be some connection there, but I have not worked it out myself. I try to avoid MHD. It's hard.
Thanks.
Great. And Nicole, do you want to ask your question, and then we'll go down to Rick?
Yeah, hi. Thanks, Daniel, for that talk. My question was just about a planet like WASP 127b, which is one of the most inflated hot Jupiters known, but its host star is not known to be evolved yet. Like, I believe it's just a very old main sequence star. So I'm not sure if you've looked into that system in particular, as to why, you know, that one is particularly inflated, since or maybe the host star is evolving, you know, but we're just not quite witnessing it yet.
Well, you can get very, very inflated planets. So you don't need them to have evolved off in order to get really high flux. Like an unevolved F star is going to beat a slightly evolved K star, right? And so, oh yeah, okay, sorry. I was trying to pull it up and Google was not cooperating with me. So yes, 1.5 Jupiter masses, almost 1.9 Jupiter radii. Nice. That's some good stuff. The Exoplanet Archive doesn't list flux, which is maddening to me. But you know, that's a very interesting one. I mean, because of the delayed cooling, if for example it recently circularized, you could, in addition to the hot Jupiter effect, have some extra heat inside, which would be really fun. I also see that this is a young star, it looks like. Wait a minute. No, I'm looking. I was looking at the wrong planet. All right, you know, I'm sorry.
No, it's okay. Yeah, I think
not cooperating with me. So
yeah. Last I checked, I want to say it was like 10 billion years old or something.
Oh, okay. All right. So
Yeah.
it's not. All right.
Right. So it's like at the end of its main sequence lifetime, I think, but it doesn't. I don't think the star shows signs of evolution.
I'm really interested in WASP 12b, which is long. So I don't have any particular comments, but I mean, like one of the things that you can do with this paper is literally just plug in the equilibrium radius. It's actually a really simple formula and see like where you are with respect to that. Like, is this an unusual planet? And it's actually like, if you look at the table here, I have the relative uncertainties here. That can get you to about, this is in percentage, just to be clear. That can get you to about a 14% predictive uncertainty just from the flux and the mass for what the radius ought to be. So it can be helpful to work out, you know, is this hot Jupiter unusually large?
Okay. Yeah, thank you.
Great. And I think, Rick, you have your hand up.
Yeah, hey, really interesting stuff there. Had sort of concept ideas going back to the days of running MESA and trying to do really cool temperature, like brown dwarfs or even Jupiter with that. And you could get some sort of like lithium and beryllium burning that would be very short-lived. But I'm wondering if like maybe there's some synergy there where you're talking about these combinations of effects where more massive planets, more massive Jupiters don't behave like Jupiter, and they might behave more like really cool brown dwarfs, and we don't know convective regions versus radiative regions. And so as they migrate in, like, I'm just wondering, like, what do you think is like maybe the next step? Yeah, in this,
So-
in trying to reconcile some of this.
I mean, I haven't so much, but Tad Kamasik has. That it's sort of his baby, is doing hot Jupiters in Mesa. I use my own somewhat simpler code that doesn't try to look for things like lithium burning. I have not heard it suggested that giant planets might have that going on before, so I haven't thought about it at all. But it's an interesting suggestion. I'll probably ask Tad. He's the one to who knows the most about this. Certainly, if you could get some early heating in the interior from some kind of lithium burning or something like that, that could potentially help. The problem is that it's a little bit like the circularization heating, because probably these planets don't form perfectly circular. There's some circularization that goes on, but they're so close in that happens very quickly early in their lifetime. Also, if they get disrupted a little bit by another planet, they'll have a little bit of eccentricity to circularize out. And it turns out when you do that kind of circularization, the heat goes into the planet almost entirely. And so you can have this big injection of heat very early in this planet's lifetime. Or potentially later if it is a disruption event in some way. But because even with the delayed cooling effect that we saw, it seems like any of those like instantaneous effects to increase the heat in the planet's interior, it shouldn't last for more than a few gigayears. But which means that any injection should be noticeable for a while, but it's not. You wouldn't use it to explain the whole set, but I think it is possible that if there's a really big heating source at some point, we might be able to pick up on it. I think the trick with lithium is that we don't know how much, like any kind of early heating like that, including the circularization stuff. We don't know how hot they are just from their formation, right? I mean, this is a problem for cool giant planets. With the hot
exactly,
giant,
exactly, yeah.
Options to heat them. And so presumably they're hotter early on, but we don't know by how much exactly. Certainly, they're going to be really hot.
Cool. Yeah. Good luck.
Great. And Vlad, you want to ask yours? I'm not sure if Vlad, I think you're still muted if you're trying to talk. Not sure if he is still there, but I think he asked earlier what the spectral classes of.
I'm sorry. Yeah.
Oh, okay,
so,
there you go.
I was muted. So, yes. Hello, Daniel. So, yeah, I looked at the statistical plots that you showed of the radius versus a number of different parameters, including the age and the metallicity. It looks like the scatter is pretty large for all those parameters. It's like between like 1 and 2, or 1.5 to half to 1.5, something like that. Yeah, and I want to discuss the reasons behind it. So the first question is that have you filtered out or have you created those plots for the stars of a specific spectral class, or you put all spectral classes together, like M dwarfs? I mean, I'm talking about hot stars, M dwarfs, G and K, and all the way to F. I think that they all show the presence of hot Jupiters. That's the first question.
Yeah, I don't think we put any M stars in this, in part because it's really hard to estimate ages for them. But so these are FGK stars. With respect to the scatter, I think the biggest problem that we have in is deriving that metallicity. People have put some work into deriving the metallicity, but it's hard to get a uniform set, and I think that's that is something of a problem that we have here with the stellar metallicity, is that unlike the ages, we didn't go through with a uniform analysis and get stellar. We rely on the discovery papers and subsequent follow-up papers to give us the stellar metallicity. And so many of them have extremely large error bars. Not all, mind you, but I am trusting these people to have good error bars.
Yeah. So the question is that if we want to discriminate between the the heating sources, basically tidal sources versus ohmic dissipation or other sources, so probably because tidal forces depend on the mass of a star. So for instance, if you compare and do this analysis for like M dwarfs, which is much low masser than has low mass, and versus like G by a factor of like 10, right? So this order of magnitude can play a big role in characterizing or factoring in the tidal heating. That's the first thing. The second is the age of the star. Of course, it's not only biometric luminosity, but it's also the probably the X-ray luminosity and the UV emission that basically the atmospheric evolution over the lifetime of a planet. So, and when we're talking about ohmic dissipation or ohmic heating, the ohmic heating, that as far as I understand, might be you mean something else. I don't know. But the ohmic heating is a result of the dissipation of ionospheric or atmospheric currents generated due to the interaction of the stellar winds with the magnetic field of a planet. So generating this and then dissipating in the atmosphere, contributing along with the extreme UV emission, the photoionization due to extreme UV emission. So now, so those two parameters, or even three effects, I would say, that EUV driven inflation versus the ohmic dissipation, tidal dissipation, they're all contribute in different degrees probably, and creating this scatter. So it will be interesting if you can somehow factor out some of the, at least for instance, by looking at X-ray emission, see that if you select the stars with the same or close X-ray emission, and see that whether that reduces the scatter. So that would be just a
one comment about the extreme UV stuff is that I think that because this is it's a surface effect. I think that for the most part, that's a bigger issue for the lower mass planets. And that might be contributing to why I had to cut out things less than half a Jupiter mass, because they start to get weird. Like, suffice to say, hot Saturns are strange. There's fewer of them and they behave oddly. You have correctly described the ohmic dissipation model that I am talking about. With regards to the uncertainties on the parameters, this wasn't exactly what you asked, but I will comment on the uncertainties of the parameters here. In general, flux is quite well determined, just because it relies on the luminosity of the star and the semi-major axis. And you need relatively large changes in flux in order to bring about a change in the planet radius. We're talking about stars can as much as double in flux over their main sequence life. Actually, more than that if they're low mass. It's a mass-dependent thing, but suffice to say, we're thinking about like big changes in flux in order to bring about a 0.1 Jupiter mass change or Jupiter radius change in radius. So I'm not really concerned about flux uncertainties. The mass uncertainties are generally perfectly adequate. They're 10%-ish, 15%, somewhere in there, which for these giant planets doesn't seem to be too much of a problem. The stellar parameters I know less about, but they usually, obviously they have to be better than the planet and the mass, and the planet mass and radius are can only be as good as the stellar mass and radius. And the age and the metallicity are like the big problems, I think, for our stuff, and that's why we had to go through and use a uniform analysis derived from Gaia data. Actually, if I failed to mention that. Being really careful to ensure all the spectroscopic inputs like the effective temperature and the metallicity were all from the same thing. I think we've done about as good a job for the age as you can do, but I certainly agree that especially for the metallicity, there's more, there's definitely some worrying to be done, especially about F versus K stars. Yeah.
Okay, thank you.
I'm not sure if I answered everything in there, but
well, maybe we can discuss later. Yeah, it's a little bit longer conversation, but it would be nice if you also add and do separate analysis like that for M dwarfs, for hot Jupiters around M dwarfs.
I don't think there's very many of those, though. I think it's not enough to do statistics. I think you just list out all 3 of them or whatever. And
but if you can put them on the plot and see where they are.
Yeah, certainly.
Great. Well, I think we are coming to the end of the hour. Does anyone else have a really quick last question for Daniel? If not, Daniel, I don't know if your email address is up there, but if anyone else wants to ask anything to Daniel, just get in contact with me and we can exchange stuff. But thank you so much again for talking with us today, and I hope you have a great rest of your week, everyone.
Yeah, thanks.
Yeah, thank you. Bye, guys.
Bye.
See you guys later. Thanks, Daniel.
Thank you.